Welcome to this lecture on gravitational potential. Have you ever wondered how physicists and engineers calculate the pull of gravity without getting lost in a mess of complicated three-dimensional arrows? Today, we are going to explore a beautiful mathematical concept that simplifies the universe. By the end of this video, you will understand how a single invisible number assigned to every point in space can completely describe the gravitational forces around planets and stars. Now that we have introduced the topic, let us understand what gravitational potential actually is. Imagine you are walking on a vast hilly landscape. The steepness of the hill at any given spot tells you exactly how fast a ball would roll down if you dropped it there. Instead of measuring the exact rolling force and direction everywhere, you could just measure the height of the hill. Gravitational potential is exactly like that height. It is a scalar field, meaning it assigns a single simple number to every point in space. Formally, it is the work done per unit mass to bring an object from infinitely far away. Because gravity is a conservative field, the path taken does not matter, allowing us to map complex forces with simple energy levels. Before we can map the potential, we must start with Sir Isaac Newton's famous law of universal gravitation. This formula describes the gravitational field, which is the force experienced by a single unit of mass. The vector g represents this field. The symbol g is the universal gravitational constant, m is the mass of the object creating the pull, and r is the distance from its center. The r hat is a unit vector pointing outward. Notice the crucial negative sign. It tells us that gravity is an attractive force, pulling objects inward, opposite to the outward pointing arrow. As the distance r increases, the denominator gets larger, meaning the gravitational field becomes rapidly weaker. With Newton's law in mind, let us connect the gravitational field to our scalar potential. Because the gravitational field is conservative, we can express it as the negative gradient of the scalar gravitational potential, denoted by u. The gradient is a mathematical operator that points in the direction where a value increases the fastest, much like pointing straight up the steepest part of a hill. By taking the negative gradient, we find the direction where the potential decreases the fastest, which is exactly the direction gravity pulls. If the potential u changes very rapidly over a short distance, the gradient will be large, meaning the gravitational force is very strong in that region. This relationship leads us to a principle called Gauss's law for gravity, which turns our concepts into a partial differential equation. Gauss's law relates the flow of the gravitational field out of a region to the amount of mass contained inside it. The divergence operator calculates how much the vector field is spreading out from a point. The symbol ρ represents the mass density, telling us how tightly packed the matter is at that specific location. The constant 4 pi g scales the relationship for our three-dimensional universe. The negative sign indicates that mass acts as a sink for gravitational field lines, meaning the field lines always point inward toward the mass rather than outward. Now we can combine our two major concepts to find the ultimate governing equation. By substituting the negative gradient expression into Gauss's law, the divergence operator acts on the gradient operator. This combination creates a new mathematical tool called the Laplacian, denoted by del squared. The negative signs cancel out, giving us one of the most famous partial differential equations in physics, known as Poisson's equation. The Laplacian measures how much the potential at a specific point differs from the average value surrounding it. This equation tells us exactly how the gravitational potential curves and bends in the presence of matter. If you increase the density ρ at a certain spot, the hill of potential energy becomes much steeper there. Poisson's equation is powerful, but we often want to calculate the gravitational potential in empty space, such as where satellites orbit the Earth. In the vacuum of empty space, there is no mass, which means the mass density ρ is exactly zero. If we take Poisson's equation and set the density to 0, we get a simpler yet equally profound equation called Laplace's equation. Physically, this means that the potential at any empty point in space is perfectly balanced. It is exactly equal to the average of the potentials in the surrounding area. There are no sudden spikes or dips in the potential landscape when you are in a vacuum. The potential changes smoothly and gradually. Let us solve a practical problem to see how this works. Suppose we want to find the gravitational potential at a distance outside a perfectly spherical planet. Because we are outside the planet in empty space, the mass density is 0, so we must use Laplace's equation. Furthermore, because the planet is a perfect sphere, the potential will look exactly the same in every direction. It only depends on the straight line distance from the center, r. We write Laplace's equation using only the radial part of spherical coordinates. Since the right side is 0, we can multiply both sides by the squared radius to simplify the expression, leaving us with a straightforward derivative that equals 0. Continuing with our solution, we rely on a basic rule of calculus. If the derivative of a quantity is 0, it means that the quantity itself must be a constant number that does not change. Therefore, the expression inside the parentheses must equal some unknown constant, which we will call C1. This gives us our first integration step. Next, we want to isolate the derivative of the potential. So we divide both sides of the equation by the squared radius. This gives us an expression for how the potential changes with respect to distance, representing the slope of the potential. We are now ready to integrate one more time to find the actual potential. To find the final potential, we integrate our expression one more time with respect to the distance r. The integral of 1 over the radius squared is negative 1 over the radius, and we add a second constant of integration, C2. In physics, we define the gravitational potential to be exactly 0 when you are infinitely far away. Plugging in an infinitely large radius makes the first term 0, meaning C2 must also be 0. By matching our formula's gradient to Newton's original law of gravity, we find that C1 equals the gravitational constant times the mass of the planet. This final answer shows that you are trapped in a gravity well, represented by the negative sign. Now let us tackle a slightly harder problem, finding the gravitational potential deep inside the planet itself. Imagine drilling a hole straight down into a solid uniform sphere. Because we are now surrounded by mass, the density is no longer 0, so Laplace's equation will not work. We must instead use Poisson's equation. Just like before, the planet is a perfect sphere, so the potential only depends on the distance from the center. We write Poisson's equation using the radial part of spherical coordinates. To begin solving this, we first multiply both sides of the equation by the squared radius. This moves the radius term from the denominator on the left over to the right side, making it much easier to integrate. With our equation prepared, we integrate both sides with respect to the distance r. The derivative operator on the left is removed, and on the right, integrating the squared radius gives the radius cubed divided by 3, plus a constant of integration, C1. Before we go further, we can figure out the value of this constant. At the exact center of the planet, the radius is 0. Plugging 0 into this equation means the constant C1 must be exactly 0 to keep the equation balanced. This makes physical sense because there is no net gravitational pull at the exact center of the Earth. With the constant gone, we divide by the squared radius to isolate the derivative. This intermediate equation tells us that inside the planet, the slope of the potential increases linearly as you move away from the center. To find the actual potential u, we integrate one final time with respect to the distance r. The integral of the radius becomes the radius squared divided by 2, and we add our final constant of integration, C2. This constant represents the potential at the exact center of the planet. Physicists find its exact value by matching this inside formula to the outside formula at the planet's surface. Notice that as the distance increases from the center, the potential curves upward like a parabola, showing how gravitational energy changes as you climb out from the core. Let us look at a diagram that visually summarizes the two different mathematical regions we just explored. In the center, you see the solid mass of the planet. Inside this region, the presence of matter forces us to use Poisson's equation, resulting in a potential that curves like a bowl. The moment we step outside the planet's surface into the vacuum of space, the mass density drops to zero, and the mathematics smoothly transitions into Laplace's equation. The dashed circles you see outside represent equipotential lines. These are paths where the gravitational potential remains exactly the same, much like walking along a perfectly flat trail on the side of a mountain. To wrap up our lecture, let us review the most important ideas. First, the gravitational potential is a powerful scalar field that simplifies complex three-dimensional vector forces into a single map of energy levels. Second, by applying Gauss's law, we discovered that this potential is governed by Poisson's equation inside massive objects and Laplace's equation in empty space. Finally, understanding these partial differential equations is not just an academic exercise. It is absolutely critical for modern technology, from keeping GPS satellites accurate to helping geologists locate underground resources. You have now covered the fundamental mechanics of gravitational potential. Great job!